Hello everyone and welcome to chapter number 5 in the three-phase induction machine course, simulation using MATLAB and Simulink. In previous chapters we covered construction, theory of operation, equivalent circuit and performance analysis. So the contents of this chapter is to simulate the three-phase induction motor or the examples we had before in the previous videos using MATLAB Simulink. And once we finish this chapter, we are going to develop a simulation model to accurately represent this motor and represent the behavior at different conditions. So we are going to generate torque speed characteristics, current speed characteristics, and we are going to look for the motor performance at under various operating conditions. Also, we are going to validate the analytical results using simulation. So this chapter consists of two videos. Video number 1 concerns with MATLAB code. Video number 2 concerns with the Simulink model. So let's start by video number 1. So video number 1 is induction machine simulation using M-code. To build the M-code or MATLAB code, we need to have a case study. So here we are going to use a specific example, and then once we finish the M-code, we are going to generalize the problem for any three-phase induction motor. So we have here a 415 volt line value, 20 horsepower, 50 hertz, 4-pole star-connected squirrel cage induction motor. We have our stator, our rotor, X-leakage stator, X-leakage rotor, our core, and magnetizing reactance. Please bear in mind that all the reactances are based on the frequency given or the rated frequency, which is 50 hertz. So we need to build the M-code using the inductance, not the reactance, just in case if we like to run this machine for any supply frequency. So he gave us moment of inertia and friction factor, and we are going to use these values when we are going to build the Simulink model or the dynamic model, but the M-code just gave us the steady state performance for this machine. Also, we have an information here about the rotational loss, so 1.1 kilowatt and assumed to be constant. So our target now just to solve this problem using analytical solution. We have the results, build an M-code, and then we're going to verify these results. And then we're going to build the Simulink model in video number 2 and check about these values. So we can solve the problem using first approximate equivalent circuit or exact equivalent circuit. So analytical solution, we are going to solve this problem using first approximate equivalent circuit, but in the M-code, I'm going to use the exact equivalent circuit because the computer will do the task. So there is no worry that's for taking any time. So that the problem can be solved immediately. So here we have all the data given in the problem and we have the equivalent circuit. So let's look for the problem if we solve it using first approximate equivalent circuit and what are the results for the analytical solution. To solve the problem using analytical solution, we need to have a specific slip. So here we are going to choose S equals 2.5%. If we are going to solve the problem for all the slip range, this is why we need the M-code. So my advice to you is return back to chapter 2 and 3 videos. And then we are going to see how we are going to solve this problem using first approximate equivalent circuit. Then you are going to compare your results with my results. I have here rotor current, stator current, input power factor, input power, egg gap power, developed power, net power, efficiency with developed power, efficiency with net power, developed torque, net torque, and also we can calculate the maximum torque results where the maximum torque and the speed at which will occur, rotor current at maximum torque, and finally we can calculate the starting torque and starting current. To start the M-code, we need to put the problem for the exact equivalent circuit in a flow-chart. So we are going to start our problem by code introduction, problem description, and initialization. We need this part if we like to return back to the problem at any time. We know what we did before. So we are going to input motor ratings and parameters, voltage, frequency, number of poles, no load loss, all the parameters, stator resistance, rotor resistance, and inductances. Inductance, not reactance, because we need to calculate the reactance based on the supply frequency. If we like to run the machine for any frequency, we can solve our problem. We are going to calculate the synchronous speed in both RPM and radian per second. And then we are going to calculate the stator impedance, R stator plus JX stator. Then we are going to calculate the parallel equivalent of R core and JXM. We are going to start a loop for the speed ranging from 0 up to the synchronous speed, and then we are going to calculate the slip for each speed. But take care of this condition. If NR equals NS, we should avoid that S equals 0 to avoid 1 over 0 gives you infinity. So we are going to calculate now the rotor impedance function of the slip. So that one will be R rotor over S plus JX rotor. From this one, we calculated the rotor impedance. We have the magnetizing reactance impedance and stator impedance. So we can calculate the total impedance. So the rotor impedance will be in parallel with the magnetizing branch and then in series with the stator impedance. So we have Z total. So we have Z total, V supply over Z total. We can calculate the supply current. From the supply current, we can use current divider rule. We can calculate the magnetizing current. From that one, we can calculate I core and IM, and also we can calculate rotor current. Once we have the rotor current and stator current, we can calculate all the machine performance, input power, air gap power, developed power, and shaft power, developed torque, net torque, starting torque, maximum torque, power factor, and motor efficiency for each slip. So we are going to stop the speed loop here and then we are going to record our results. So let's start MATLAB code, and remember our target is to plot the torque, current, power efficiency and power factor versus rotor speed. So we need to look for the machine performance for the range of the speed from 0 up to the synchronous speed. So we are going to start our problem by making the initialization, the starting, the clearing, and then we're going to input the data. We know that's the voltage, the number of poles, the supply frequency, and then we're going to calculate the omega, which is 2 by f, number of phases 3, and then we can calculate the synchronous speed in RPM and in radian per second. So someone can say that I don't like to put these values or specific values. I need to have a general M-code or genuine M-code. So here, for make it easy, rather than every time when I'm going to run this program, I'm going to enter all the data, but you can put all of these things are variable. So you can make any machine if you like. But here I use this example. So specifically we have phase voltage 415 volt over root 3. We have number of poles 4, 50 hertz, and we can calculate the synchronous speed. The second step is to calculate or to input all the parameters. R stator, L leakage stator. So how do you calculate the L leakage stator? Given in the problem the reactance is 50 hertz, so X over 2 by F can give you the inductance. So the inductance of the machine, L leakage stator, for example, here is 2.86 millihenry. So we are going to substitute that one or find that one at specific frequency. We need that one at the frequency 50 hertz. So later on when we are going to calculate it, we have X stator will be L stator multiplied by omega. So we entered all the parameters. Now we can calculate the stator impedance, which is R stator plus JX stator. And the magnetizing impedance will be Z magnetizing, will be the parallel equivalent between R core and XM as we did here. So we finished the stator side. Now we are going to start the loop. So for NR ranges from 0 up to 1500 RPM, and I use a step 0.5 RPM as you can see here. So I'm going to start that one for I, it's a variable, from 1 up to the length of NR. We can calculate the slip, which is 1 minus NR over NS. So S equals NS minus NR over S. This is the same equation. So when we are going to check if S equals 0, I'm going to put S a very small value, S equals 0.001. So we are going to substitute that one in the rotor impedance. So Z rotor will be R rotor over S plus JX rotor, and then we are going to take the parallel equivalent between the rotor impedance and the magnetizing branch, and then we are going to have the total impedance, which is ZSX function of this slip will be the parallel equivalent of the rotor and magnetizing branch plus the stator impedance. So once we have that one, we can calculate the stator current, V supply over the total impedance, and then we can calculate the rotor current using current divider rule. So I stator multiplied by Zm over Zm plus Zr of I, function of I. From this one, you can calculate the torque, the power output, the power net, the torque net using the equations we had before in the previous chapters, the angle of the supply current to calculate the power factor, where the power factor is cosine this angle, power input and the efficiency for the delivered power or developed power and the efficiency for the net power. And also we can calculate the stator copper loss and rotor copper loss. That one for each slip. When the loop ends, we are going to plot torque speed characteristics and torque current characteristics, and also we can have torque power characteristics, power input, power output, efficiency, and power factor. But we feel that you explained that one quickly. So we are going to look for the results, and then we are going to move to the MATLAB platform and look for this one in the M-code or the real M-code. So let us examine the output from this M-code. We have the torque speed characteristics as we anticipated. We have a starting torque, something in the range of 68.6 Newton meter. We have maximum and we have a stable region. So specifically at slip 2.5%, we are going to look for the results. So at S equals 2.5%, so the speed is 1462.5 RPM and the torque is 71.2 Newton meter. We are going to record these values. So at maximum torque occurs at 1268 RPM roughly, and the maximum torque is 191.2 Newton meter, and the slip for this point is 15.5%. What about the current? So we have here the red color is the rotor current, the blue color is the stator current. If you look here at synchronous speed, the rotor current is 0, but the stator current has a value which is a magnetizing current. At starting point, the starting rotor current is 108 ampere and the starting stator current is 110.4 ampere. Looking for the stable region and specifically at slip 2.5%, so the rotor current is 17.1 ampere. I'm speaking about the magnitude here, and the stator current is 20.6 ampere. If you look for this point, we have a magnetizing current at this point is 8.4 ampere. Definitely in the exact equivalent circuit, so this value is close to this one, but if you are going to use first approximate equivalent circuit, the magnetizing current is constant through the range. But here it depends on the stator current and the rotor current. So the difference between them is the magnetizing current. Regarding the current at the maximum torque point, so we have here the rotor current is in the range 69.6 ampere and the stator current is 73.44 ampere and the speed 1267.5 RPM. What about the power factor and efficiency? So we plotted the figure from 0 up to the synchronous speed. If you look here, we have two axes, the left axis and the right axis. So the left axis to represent the power input and developed power, the blue color, and the right axis efficiency and power factor, the red color or orange color. So the solid line for the left axis will be the developed power or output power. So starts at 0 speed, there will be 0 power. At synchronous speed will be 0 power, and we have a maximum developed power at this point. Regarding the input power, which is the dashed line, at synchronous speed we have 0 input power, but at 0 speed, at starting point, all the power is consumed as copper loss in the machine. That one is very huge power. Yes, something strange, but the machine depends on the energy because that one is very short time. So the energy consumed at this point will be very minimum because that one is something like millisecond multiplied by this power. So the energy consumed is very low. As the power is increasing, so we are going to have the efficiency curve and the power factor curve. Look here that this point will be the starting point. We have here very low power factor at starting, and if we look for the stable region, we need to extend this figure to the stable region, and specifically at slip equals 2.5% or speed equals 1462.5 RPM. The output power is 10.9 kilowatt and the input power is in the range of 12.92 kilowatt as anticipated. Looking for the power factor and efficiency is something like 84.4%, which is a solid line here, and the dashed line give you the power factor at this speed range will be 0.872 lagging. Definitely you can calculate the power factor, the efficiency, input and output at any point, something like the starting, the maximum, using this graph. So here we calculated at this speed to compare with the analytical results. So now we need to go to the MATLAB platform to make a performance evaluation using this M-code. Also, we need to learn how to plot such graphs. As you can see here, we move to the MATLAB platform. This is our M-code. So the M-code is started by introduction. This introduction includes what is the code, what is the purpose of this code, what is the function we are going to calculate or what we are going to evaluate. So also you can add in the introduction the date, the MATLAB version, whatever you like to add information here. So then I started my code by initialization or clearing all the variables. So by using a clear function, and then a clear command window by adding the function CLC. Then I'm going to input all the data, voltage, number of poles, frequency, and so on. So someone can say that I can make them variables. Yes, 100% true. But while I'm running this code or testing this code, it's difficult every time to input all the values. So I put it inside the code during that testing time. So voltage, number of poles, frequency, I calculated the angular supply frequency 2 by f, and number of phases is 3. Why you have number of phases 3? We know that the machine is 3-phase. So just in case in the future I like to run this code for 5-phase machine or something like that. Synchronous speed, I calculated in RPM and in radian per second. Then the second stage is inputting the machine parameters. Stator resistance, stator leakage inductance, rotor resistance, rotor leakage inductance, magnetizing inductance, core resistance, and rotational loss because it's constant. Then we are going to calculate the stator leakage reactance, the rotor leakage reactance, and then magnetizing reactance. So we know that one from the problem, why we calculated as inductance, then we recalculated as reactance. Assume we like to change the frequency, so we need to calculate XS, XR, XM at specific frequency. The third step is to have impedance calculation. So Z stator equals R stator plus JX stator. So the MATLAB understands the rectangular form. And then we calculate the magnetizing impedance, the parallel equivalent between R core and XM. So that one is ZM. Then we are going to start calculating the rotor impedance, function of the slip. So we are going to write the range of the rotor speed as x-axis, nr equals 0 up to ns in a step of 0.5 rpm. As you can see here, so 0 up to ns in a step of 0.5 rpm. Then we are going to start the loop by the length of nr here to calculate the slip value. So the slip equals 1 minus nr function of this I over ns. So the slip will be variable. We need to avoid s equals 0 to avoid any singularity in our calculation. So if s equals 0, so s equals 0.001, I choose a small number. Then we are going to calculate the slip for this value. So Z rotor equals R rotor over S1 plus JX rotor. Then we're going to take the parallel equivalent between the rotor impedance and magnetizing branch. So please note that we solve this code for exact equivalent circuit. Then the resultant will be added to the stator impedance. Then we have the equivalent impedance of this motor. I call it ZX, function of I or for a specific slip. So now we can calculate the stator current. The stator current function of the slip is a supply voltage over the total impedance function for the same slip. The rotor current will be the stator current multiplied by the magnetizing reactance over magnetizing reactance plus rotor impedance. That one is a current divider rule. Then we are going to calculate the torque because that one depends on the rotor current. So the torque function of this slip will be number of phases multiplied by the absolute value of the rotor current squared multiplied by R rotor over S over omega S. So if you remember, the torque equals B gap over omega S. So that one will be 3I rotor squared R rotor over S omega S. Then we can calculate output power. So output power will be torque, developed torque multiplied by omega R. Then we can calculate the net power, which is the output power minus the rotational losses. So we can calculate the net torque, which is P net over omega R. So we need to calculate the angle of the supply current to calculate the power factor. So here the power factor will be cosine the angle of the current. Assuming that the voltage has an angle 0, if the voltage has an angle, so the power factor will be cosine theta V minus theta I. What about the power input? So the power input is 3V supply multiplied by absolute value of the stator current multiplied by the power factor. Now we can calculate the efficiency, net efficiency, and the efficiency from the developed power. So the efficiency is power output over power input for a specific slip, or net power over input power for a specific slip. Also, if you like to calculate, you can calculate the stator copper loss and rotor copper loss 3I square R. Stator, that one is the stator copper loss, or 3I rotor square or rotor, that one is the rotor copper loss. So the loop ends here. Now we are going for the result stage. The last stage is the result stage. We need to plot torque, current, power, efficiency, and power factor versus speed. And when we plot these figures, we are going to find the values at specific slip, which is 2.5%. So if we look here, we are going to start by torque speed characteristics. So we are going to generate a figure by writing the command figure. We call it figure number 1. So we are going to put the torque as the y-axis and the speed is x-axis. So we are going to write the command plot nr and t. So this one is going to give us the torque versus speed for the range from 0 up to the synchronous speed. So we are going to write here the y label torque in Newton meter. The speed will be the x-axis, will be the speed in RPM. So if you like to add the title for this graph, you can add title, whatever you like. So moving to another figure, we are going to have stator and rotor current for the same figure. We are going to add a figure, we call it figure 2. Stator and rotor current will be y-axis, but they are two functions now. Let's look how we are going to do it. And the speed will be x-axis. So plot the speed and the absolute value of the stator current. So we use the function ABS, absolute value for the stator current. Then we are going to use the function hold. You can see here we have what we call it hold. Hold the figure. Then plot the speed as the x-axis and the absolute value of the rotor current. We are going to put X label, which is the speed in RPM. The Y label will be current in ampere. And then we are going to add a legend if we like, data 1 and data 2. We are going to add it by ourselves when the figure will run. For the third figure, we need to have output power, input power, efficiency, and power factor. But there is a problem here. Output power and input power will be function of kilowatt, and the efficiency and power factor either will be from 0 to 1 or something like percentage. So how we are going to plot a figure like that one? We are going to start by adding a figure, figure number 3. We are going to put X label will be the speed in RPM. Then we are going to start plot the speed as x-axis and the power output divided by 1000. This means that we are going to have the y-axis in kilowatt. And then we are going to add hold. We are going to add the input power. So now we can plot both input and output for the y-axis. How we are going to add the efficiency and power factor? That one will be something like 8, 9, 10, 11, 12. So to add the efficiency and power factor, something like 0.1, 0.5, 0.8, that one will be difficult for the same axis. So we need to add a right axis. So Y label, we added for the left axis power in kilowatt. So we are going to add a new right axis, we call it Y axis in the right side. So the left side will be for the power, the right side will be for the power factor and efficiency. Then once we added that one, so MATLAB understand now whatever I'm going to plot will be in the right axis. So plot the speed and efficiency. Plot the speed and power factor. So do we need to add hold here? If you add hold again for the same figure, figure number 3 is going to release the hold. So hold is added one time, as you can see here. So we added hold, plot the input over the output. We added another axis in the right side, plot the efficiency, plot the power factor. So also we can add the label for this one, will be efficiency and power factor, and we can add the legend for this figure. At this time, the code is finished and we can run the code. To run this code, we are going to click on the play button or run button here. But if there is any mistake in your code, the MATLAB is going to give you alert about that one. But if your code is 100% correct, you are going to see the results. So we expect to see the figures for the torque speed, current speed, and power speed or power factor and efficiency speed characteristics. So click on that one. I'm going to find the three curves, figure 3, figure 2, and figure 1. So figure 1 represents the torque speed characteristics as we anticipated. So that one is the x-axis, the speed, and the y-axis, the torque in Newton meter. For figure number 2, we are going to have stator current, absolute value for the stator current, which is the blue line, and the rotor current, absolute value for the rotor current, which is the red line. Going for figure number 3, we are going to stay a while with this one. We are going to adjust the figure as we saw in the slides. So first thing that we can move this legend anywhere. So we are going to change the label here. So we are going to add data number 1 is output power. Data number 2, input power. Data number 3 is efficiency. And data number 4 is power factor. Definitely you can add any words you like here for your legend. So I'm not happy with the colors, I'm not happy with the line width. So what we're going to do, we're going to click on this arrow here. And that one is going to show us a pull down menu. So if I click on the figure or the curve like this one, so I'm going to see here in the right side or the left side, it depends on the screen you have. So I'm going to double click on that one. I'm going to see that one here. So to the top, I see that one with the color blue and the line width is 0.5. So I'm going to change that one to something like 3. Look, so that one is changed immediately. For the power input, that one is red. I need to make it blue as well, like the output power, but I'm not going to make it solid line. This time I'm going to make it dashed line. And the width will be the same, like the output will be something like 3. And that one is reflected immediately to the legend, as you can see here. Regarding the efficiency, we're going to make that one something like orange color because that one is the right side. And then I'm going to change the width to something like 3. And for the power factor, because that one is the right side as well. So let me click on that one. So that one, I'm going to make it any color we like, but I'm going to make it the same color like the efficiency because that one follow the same X. And then I'm going to choose that one as a dashed line. And then I'm going to make that one 3. So as you can see here, that one is reflected to the legend. Fine. I'm not happy with the text. So that one 0, 500, 1000, 1500. Also later on, I like to have a specific value or maybe a range from 1000 to 1500 for the speed range. So how are we going to do that one? So I'm going to click on this arrow and then I click on this X here. So it's going to give you a menu like that one. So first thing that if you are not happy with the font type, font size, you can change it. So I'm going to change that one from 10 to 12. So as you can see here, the font change it, font size change it. Regarding the text, so I'm going to minimize that one. I'm going to look for the text. So that one 0, 500, 1000, 1500. So either you change the number of cells or you can do that one manually. Click here, add, click here, add, click here, add. So that one shows to you 7 cells from 0 up to 1500. Okay. You can do the same for the y-axis if you like. So going to the next one, which is the rulers. So that one from 0 up to 1500. Now I'll keep it. I'm going to return that one later to change the range and also for the y-axis. But I'm going to the next one, which is a grid. I'm going to make X grid and Y grid to make my figure more clear and neat. So labels, we don't have X label, so I'm going to adjust that one. So here I'm going to add X label. That one shows to me that X label. I can write here whatever I like. Either you can do it inside the code or you are going to do it here. Speed, RPM. Also, you can add a title for your figure. So if you are happy with your figure now, so you can make edit, copy figure, you can paste it in any platform, something like Word or PowerPoint. You can do the same for the torque speed characteristics and the current speed characteristics. So what about the speed range? If I like to change the speed range. So I'm going to click on that one again. Click on the rulers. So here, rather than to write it from 0 to 1500 RPM, I'm going to write that one from 1250, for example, to 1500 RPM. So that one is changed. Also, you can change the text between 1250, 1500 to change the grid. So you can find that one here. This is a graph or this is a range you are looking for. Okay. I'm going to disable this arrow, close this menu, and then I'm going to look for this curve or this data. If I like to extract a value from this graph, I'm going to do it. So I'm going to move on my curve here. I'm going to find a small circular dot. It's moving with me. When I stop for any point, I'm going to see X and Y. So that tells me the speed is 1373 and the power output is 24 kilowatt. If I move forward, so I can have another speed, 1436. Assume I want the results at slip 2.5%, which is 1462.5 RPM. So I'm going to move until I find this value. So here that's 1463, which is close to that one. So now the speed is 1463 and the power output is 10.78 kilowatt. For the power input, so that one is close to this value. So that one is 13.35 kilowatt. For the efficiency, so we are going to move until the speed we want. So something like that one. So the efficiency is 84.4% and the power factor for this point, roughly something like 0.87. As you can see, that one is not easy task. What will be the case if I need a specific value at 1462.5 RPM? What will be the torque, current, power, output, input, efficiency, and power factor? So we need to go to the MATLAB command window, and then we are going to see how we are going to find these values. So if we return back to the MATLAB command window, so we run our M-code, we have the graphs, but we need to look for the results. So if we write here NRN, so that one is going to give you all the values for the speed from 0 up to 1500 RPM. We know at slip 2.5%, the speed is 1462.5. So we are going to search for the counterpoint here. So where is 1462.5? So that one shows to me that 1462.5 will be at the counter 2926. We need to record this value, right? So how we are going to make sure that we are correct? We are going to write here NR of 2926. That one should give you 1462.5. So we're going to use this value for any other thing. So for the torque of 2926. So that one is the developed torque. That one is 71.2 Newton meter. The stator current, if I write I stator of 2926, so that one is going to give you the stator current in rectangular form, real plus imaginary part. But I don't want that one in this way. I want the absolute value. So absolute of I stator for 2926 will give you the current magnitude at this point. So the stator current is 20.62 ampere. What about the angle? So we are going to write angle of I stator 2926. So that one gives you the angle is minus 0.5122. Strange. The angle is minus 0.5. Minus is correct because we have lagging power factor and we assume the voltage is zero angle. So that one is okay. But 0.5, that one is in radian. So to have it in degree, so we are going to multiply the answer by 180 over pi. So that one gives you the angle in degrees, minus 29.35 degrees. You can do the same for the rotor current, and you can calculate, for example, power output of 2926. We can have the result here. So that one will be 10.9 kilowatt. You can do the same for the power input, for example, eta of 2926. That one give you the efficiency, which is 0.84. You can multiply that one by 100%, so 84.4%, and also the power factor. What is the maximum value for the torque? What is the starting torque? So let's start by the starting torque. So to have that one at starting, so NR at point number 1, so T of 1 represent the starting torque. So we have a starting torque for this machine, 68.64 Newton meter. Starting current, absolute value of I stator of 1. So that one gives you the starting current 110.4 ampere. So you can do that one at the point of the starting. What about the maximum? So if we look here, we have two options here, or two ways you can find the maximum torque. So you can list the torque, and you are going to search for the maximum point by yourself. This is one of the ways, right? Or you can ask the MATLAB to search for you the maximum. So maximum of T, right? So that one give you, right, give you maximum of T, sorry. So the MATLAB is going to correct you directly. I wrote here M capital. So the MATLAB said that it should be small letter. So that's good. So we have the maximum 191.2 Newton meter. So we are going to return here to find that one, 192. We'll look for that one. We're going to find the point for the maximum, 192.2. So that one is the point we are going to search for the maximum here. So that one is the maximum point. So here we have the maximum point. So we can see that the maximum point at 2536. So let's check. We are going to write T of 2536. So that one is going to give you the maximum torque, which is correct. So now we are going to calculate the speed at maximum torque. So NR at 2536. So this is the speed for maximum torque course, 1267.5. You can calculate the slip. What is the current at maximum torque? So absolute of I stator at 2536. I'm going to close that one here. So this is the current at maximum torque, 73.44 ampere. So we are going to list all the values we need, and then we're going to return back to our slides to compare with the analytical results. But before returning back to our slides, we are going to test our code as a performance evaluation if we change constants or parameters. So here I disable the current, power factor, and efficiency curves, and we are going to focus only on the torque speed characteristics. So let us run our code. So we have the torque speed characteristics as we anticipated, and then I'm going to hold this figure. Return back to our code. What will be the case if I change the voltage rather than to be 415 volt to be 380 volt? Let's run. So we can see here that the torque speed characteristics, starting torque is reduced, maximum torque is reduced, we have the same synchronous speed. I'm not going deeply in the performance evaluation, I'm just showing you here that if you like to make a performance evaluation, what you can do with your code. So what would be the case if we change the frequency to 40 Hz instead of 50 Hz? Run. So this means synchronous speed is changed, maximum torque is changed, and starting torque is increased as well. So what will be the case if we change that one from 4-pole to 6-pole? So for the 6-pole machine that you have more maximum torque, more starting torque, so that one it depends on the machine performance or the parameters. So I'm going to close that one. So now you can see how to compare between different cases. And that one at 380 volts. So I'm going to return to the original case, 415, 4 poles, 50 Hertz, and I'm going to run the code again. So we have the torque speed characteristics, the original one. I'm going to hold the figure and return back to our code. I'm going to change the rotor resistance from 0.32 ohm to 1 ohm, for example. Let us see. So now we have torque speed characteristics. Starting torque is increased and the speed is going towards this direction, or the maximum torque occurs at lower speed, but almost the same value. So as you can see here, the maximum torque is something like 191. So the maximum torque here is almost the same value, but the starting torque is increased. You can apply the same concept for the current curves, power factor efficiency. So that one just to show you how to change the parameters in your code and find the performance evaluation. Back to our slides, we had these analytical results before. We solved the circuit for first approximate equivalent circuit. And now we can compare the results from our M-code. But bear in mind that M-code is performed for exact equivalent circuit. The frame box here shows the results at S equals 2.5%. So the speed is the same. And we have the same angular speed. The rotor current is close in both cases, but the stator current has some difference, and the power, efficiency, and net torque. For the maximum torque, we have the maximum torque occurs at speed something like 1268 RPM, which is close to the analytical results. But the rotor current at maximum torque is something like 69 ampere from the M-code and 70 ampere in the analytical results. But the maximum torque, developed torque, from the M-code is 191.2 Newton meter, but from the analytical results something like 200 Newton meter. The starting current from the M-code is 110.4 ampere, but for the analytical results something like 116 ampere. And that one is going to be reflected in the starting torque as well, where the starting torque in the M-code is 68.64 Newton meter and 71.1 Newton meter. So code or the simulating the machine using MATLAB is going to give you an idea or more depth about what happened inside the machine for any slip point, as we notice here. And the analytical results is easy to calculate for 1 point, 2 points, or 3 points, but we cannot calculate for each point for the slip. So this is why we need a simulation using MATLAB code. What will I watch in video number 2? In video number 2, we are going to look for the dynamic simulation using Simulink. See you in the next video.